the presentation that I'm going to give is about some parts that are very important for my microscope, and in particularly, not for just regular microscope, all microscope, focus on the kind of technology that we will need to do the kind of methods and the kind of analysis we will learn during the course. So it's not intended to cover the whole different things. I think I don't have to convince any of you about how important is microscopy in life science, and in particular biomedical. And most of you know that, resolution, I'm not going to explain in detail, but resolution in any confocal microscope, epifluorescent microscope, it's more or less with the best objective we have on the 200 nanometer in the XY axis and on the 500 nanometer in the zeta axis. And we have several technologies that can go to this limit of resolution. And for the last 20-15 years, we start to overcome this diffraction barrier by, super resolution technique that enable us to go to, tens of the nanometer, and nowadays to the nanometer resolution. And we will learn more about these new techniques on the Wednesday. And between today and tomorrow, we will be using mainly confocal and multiphoton microscope to do, fluorescent correlation techniques, and also to do FLIM and spectral imaging. So an epifluorescent microscope needs basically few parts, in particular a source of light. The light will be basically passing through a dichrom mirror, and this dichrom mirror will be used to split the excitation light and the emission light, and then we will need some optics, and the optic will focus our light of excitation in our sample, our specimen, and then the emission will be anisotropic. We will collect with the same objective the light, and the dichroic will make a job to split excitation and emission, as I mentioned before. And then we will have our detector that in an epifluorescent microscope can be a camera, but also can be our eyes, etc. So basically, when we do epifluorescent microscope or wide field microscope, our eyes are collecting light from different focal planes, and we cannot handle with that. A way to overcome this is the confocal microscope, and in the confocal microscope, the big difference is basically the introduction of a little hole that we call pinhole, and this pinhole is rejecting, right? If we focus the light before, the detector, it will reject point where apart, above or behind of the focal plane that we want to study. And this is the main concept in confocal microscope, and it will be fundamental for the experiment that we will learn today about fluorescent correlation spectroscopy, because we need to define a volume where we can study the moving of molecule in and out of this volume. And Enrico in the next talk will explain in detail this kind of experimental technology. I got funny these lenses, which are basically lenses anti-fatigue or to prevent myopia, in which what we have is a collection of pinholes that will reject all the light that we don't want and only the light that we want to focus, and our attention will be only focused on that. And this is not other thing that basically what we do in the confocal microscope, and in particular in the spinning disk, when we have many pinholes moving together. But with this kind of technology, we can go from wide field microscopy. When we focus the light on a cell, we will see, the many different focal plane, and this is the reason for why we got this blurry image. When we switch to confocal microscope, we can scan in zeta, and we can have many different focal planes, and the image is more crispy. The same with spinning disk. Even though it's a little bit less in resolving the zeta, still you have a very good resolution, and you can have way more speed in the acquisition, because speed in this is focused, it detect on cameras. And then we will learn a little bit more on multiphoton and some other techniques like TIRF, etc. So just to mention, because in the third day we will learn quite a lot about super resolution. You know, there are different kind of technology. This technology deserved the Nobel Prize in 2014. Basically, we have what we call true or functional super resolution, and basically they can perform, they can break the barrier of the diffraction by different techniques, looking at the deterministic super resolution like STED or Resolve, etc., or by stochastic solution. And Fernando Stefani, Giuseppe Di Cidomi, and Luca Lanzano will tell more about these technologies. So, in summary, what we need for a confocal microscope are basically these four parts. So we need light. Usually for a confocal microscope are based on lasers. We need something to move our beam, because when we collect the light through a pinhole, it's only from one spot. We reject the other information, and we are collecting the light with a detector that only can detect a single spot. And we will see in a minute what is this kind of configuration. And then we need detectors, and we need some other parts like optics, electronics, etc. So speaking about, reviewing about lasers, well, there are many different, approximation, helium neon lasers, argon laser, diode laser, or solid-state laser. In particular, diode lasers and solid-state laser today are taking the market because they are very, very good. Diode lasers are very cheap and they're very stable. But most of these lasers are conceived as a continuum wave. So we have a continuum amount of light over the time. They are not pulses. And for lifetime imaging, we need to have pulses, because between pulses we will collect photons that enable us to understand what is the lifetime of the fluorophore. For these kind of purposes, there are different options. We can either modulate some of the lasers. There are different strategies. I'm not going into detail, but we can use some strategic like attenuator, etc. But we do have some lasers like supercontinuum laser, white lasers, that can cover really a long range of excitation from 390, 400 nanometers to a couple of microns. And they are by default pulse, usually at the 20 megahertz, and they can basically be used to perform lifetime. The only drawback is that you need to basically isolate the light that you want to use, and to do so you can use different strategies, but bandpass filter is the most common. Then we have two-photon excitation lasers, multi-photon excitation lasers. In particular, is this laser. These are different brands that I found in the market. In particular, in Uruguay, we have two. One is from Spectraphysics, the MyTi with the deep sea model, and then we have this Carmel 780. This is a Faber base with a single excitation. The other one is a tunnelable laser, and all of them are pulse, very intense in power, and most of the two-photon laser are titanium sapphire crystals, and this has usually a repetition of 80 megahertz. But for example, our femtosecond laser with a fiber is 50 megahertz. So you need to basically be aware of what is the frequency, and you will set up your microscope with the frequency that you have. Then there are some new lasers who has expanded range, and these are able to go to 1300 microns or 1400 microns, and these are very useful, for harmonic generation, but also for fluorescent proteins, because usually with the regular two-photon microscope you reach to 2000, and 1000 is still short for some, more red fluorescent proteins. And with this kind of lasers are very, very, very good and also very powerful. I need to stop a little bit by two-photon excitation because we will use it a lot, and I will like to introduce what are the key concepts to understand why two-photon excitation occurs. And well, we deserve all the theory about two-photon excitation to Maria Oppenmeier, who got the Nobel Prize in 1963 for her work in the understanding of the atoms and the nuclear atom. And basically, I am not going to the details of the formula that describe the cross-sectional absorption for two-photon excitation, but what is important is that the excitation depends on the power of 2 of the laser that you are using and also of the frequency. And if we go to a review what is the, in the literature, the two-photon excitation difference between one-photon excitation, in the Shklovsky diagram, as Dave showed before, we have, fluorophore in the ground state, and when we hit this fluorophore with the proper light, it will excite, and then after some fast reorganization, it will fluoresce, and this cycle will go over and over until we damage the fluorophore. In two-photon excitation, what the literature says is that we use 2 photons of the half of the energy. Let's say if we have 400 nanometer here, we need to have 2 photons of 800 nanometer, sorry, and the fluorescence will occur anyway. But to understand better these 2 things on how this occurs, we need to take into account time and space. And why it is important? Well, the excitation occurs in the femtosecond nanos time scale, right? So when 1 photon hits the molecule for two-photon excitation, this have basically an intermediate or excited state which need an extra photon in order to get there. And if this second photon didn't come within this femtosecond time scale, this will never happen. So putting together, all the energy impulses is the main reason for why we need to shrink our photons in a short pulse, usually broader, no more broader than femtosecond times, like less than 100 femtosecond, in order to increase the statistic of this, intermediate state before this go down and you can stabilize. And the other important thing for the two-photon excitation is that we need spatial compression. So we need that this pulse will be focused on our spot, and this increase a lot, the energy in this spot, producing excitation at this limited space. And this tells something which is very important of two-photon excitation, which is that two-photon excitation is intrinsical confocal. Because in any other place, before or after this spot, you don't have enough energy concentrated in time and in space in order to produce excitation. And this is basically the reason for why two-photon is very, very powerful. The other important thing is, when you penetrate in the tissue, you have absorbers like hemoglobin or melanin or water, and there is a special window between 600 to 1200, which is very transparent. So there are not that much absorption of these molecules, and this is why two-photon can penetrate more in the tissue. And the other important thing is the dependence of the scattering coefficient, which is on the power of 4, and this is the reason for why, as larger the wavelength, less scattering. I want to make a point here. This can eventually don't see like a big change, but this is logarithm scale, and we are going from to the -2 to the plus 3 here, so this is really, really huge changes in the scattering and absorption. And the important thing is, as I mentioned just a minute before, is this intrinsical confocality of the two photon comparison with the wide field enables to less photo bleaching and less photo damage in our sample, and this is an important feature. So for regular laser scanning microscope like confocal, stealth, or multiphoton, we use basically scanning. And these are some of the microscopes we have in Uruguay, like 800 from size, or 880, or this is the diver microscope that we are building here, and we will visit the institute, so you will have the chance to learn more about this microscope. And scanner can be basically formed by two mirrors that has basically motor that can move these two mirrors very coordinatedly and basically make a raster image. These are the different ways that we can scan, like galvanometric scanners, resonance scanner, which are very, very fast because they have a fixed frequency, right? And they can go way faster than the galvanometrics. And then we have polygonal scanner like this one, or acousto-optic deflectors that we can also use for other purposes like attenuation, and you can move a beam along an area. Another possibility to scan is to use stages, like piezo stages, that you can move. And these are very useful, for instance, in some super resolution application. Fernando Stefani will talk about influx, and this is one of the ways that they move the sample. These are very good because they have nanometer resolution, but it's a little bit more slow in the movement of the sample, and for instance you can do low rate of image acquisition. So the two configurations that we have usually in the confocal microscope can be the scan and non-the-scan. And what this means is what I have this cartoon in the slide to explain. So basically, we have detectors and we have a light, like it can be 2 photon or single photon. And usually, what we do is we have some optics, like a dichromatic mirror here that can split excitation and emission. And then we pass through our scanner, who will make the raster scanner in our image. And we need a set of 2 optics that are called scanning lens and tube lens, which enable you to basically scan your sample, moving the beam in the back aperture of your objective and making the focus scan the whole field of view, right? When the light from fluorescence coming back and pass through the scanner and then pass the dichromatic mirror, the light after the scanner is stationary. It's no longer moving, right? It's quiet and straight. So basically, you can put a pinhole and focus the light and pass through the pinhole in order to do confocality. This is the regular way that all confocal microscopes work, and basically, then you need to just, if you want to have more than one channel, you can use, another dichromatic mirror, or you can use some other strategies like, acousto-optic modulator, IOTF, etc., that enable you to collect different ranges. But this is the configuration. One difference with 2-photon excitation is we can take advantage of not using a pinhole, right? And if we don't use a pinhole, eventually we can collect the light before the scanner, right? So we will do the same configuration. We will use the laser and then the scanner and then the scanning optics to focus our light in the sample. But this dichromatic mirror, which was basically in the other position here, you see, after the scanner, we can set this dichromatic mirror between basically the scanner and the objective of the scanner and the scanner optics, but not after. And the reason for why is because we don't need a pinhole, right? So it's already confocal. It's coming from this little volume. The only important thing is this beam here will be moving. It will be, moved by the same movement that we are doing with the scanner. So basically we need to use some optics on front of the detector in order to focus the light and hit the center of the detector, and that's it. And why to bother? Why to bother to do that? Well, the thing is, as you save steps in optical path, you gain more photons in the collection. So the reason for why sometimes in two-photon microscope we use non-scan detection is because we save a lot of photon, avoiding to passing through the scanning lens, avoiding to passing through the scanning mirror, etc., right? So these are the two main configurations. Just to review the Galvano scanner, which are the one that we will be used for our experiment on fluorescence correlation spectroscopy. They are very, very good because they are linear and they have really high resolution, and they are, even when the frame rate is low, the temporal resolution within the pixel and within line is enough for the dynamics that we will be measuring in within the cell. And another alternative is the spinning disc, which is based in this NIPO disc, in which we have many, many pinholes, and we can put this on front of our camera, and we will collect, information from many, many pinholes with an array which is in a camera. Then we need detectors, and speaking about detectors, the two main detectors that we will be speaking along the course are the PMTs, photomultipliers, or the APDs, or avalanche photodiodes. The PMTs can be, they are very, very useful. They are, analog detection, and they have a relatively poor quantum efficiency, but depending on what are the material they are built, they can have really long range of, different wavelength detections. So this is basically the sensitivity over the wavelengths, and you can see that, there are many, many different opportunities in the market. In particular, I want to point the gallium arsenide phosphodiene, which are the most used today, and they are really, really sensitive, up to 50% or something like that. And they are very linear within the range that we will be using for most of our application, for 400 to 650 or 700, and we will be speaking a lot about this detection. The other are the avalanche photodiode. These are silicon-based detectors. They are way more sensitive than PMT. This is a comparison between APDs and PMT. You see that you have higher quantum efficiency, but you see that they are also more narrow in the detection range they have. So just to understand a little bit about the technology, well, we have a cathode and we have an anode, and then we have, diodes. And when we move our gain in our detector, what we are doing is we are moving the potential that we put between cathode and anode, and then there are some electronics to, make a gradient of different potential between the different diodes. And when the photon hits the photocathode, this releases a photoelectron that will hit the first diode, and in the first diode, it will start to amplify the signal. And how much this can be amplified? Well, from one photon, we can have like a 70,000 photoelectron. So we amplify quite a lot. And this is something that we will take into account when we will try to do, fluorescence fluctuation spectroscopy using analog detection. Why these are very useful? Because they are very fast. So we can use these for counting photons. These are important for photon counting, for fluorescence correlation spectroscopy, but also for FLIM measurements. And they can be read really, really fast, which is fundamental for lifetime measurements. And they are very good in signal to noise. The other important thing is, someone is calling. The other important thing is they have the area of detection are larger than in the APDs, and this make the life of the customized microscope much simpler. In the avalanche photodiode, these are basically semiconductors, as I mentioned before, silicon-based, and they have a positive and a negative dope regions in which, depending on the power we apply, we can basically straight amplify from one photon many photoelectrons. And you can see that here that applying a really long range in the voltage, we don't have that much dark current, which means basically dark noise. And these are very useful detectors in the market. Nowadays, there are combination of PMTs and APDs, and these are hybrid detectors. They are, very useful because they have really low transit time, so they can be read very, very short. They have high quantum efficiency, and they are very useful for FLIM and for some other application too. So after finish with the single point detection, we can have also arrays like CCDs and CMOS cameras, and these are basically two different technologies that we will review in a second. And then also we have some group of detectors. These are PMTs, but these are arrays of PMTs or APDs that can be used or read as a little camera, right? So one case is the 80 detector in the size microscope that can basically use as a spatial camera, and in the LFD they develop a technique in order to study fluctuation within this detector, and then you can apply many of the tools that we will learn. And on Wednesday, Giuseppe De Vici-Domini is also going to talk about an array of APDs for image to do all this imaging like FLIM, FCS, etc. with an array, and we will learn how important this can be for some application. So speaking about how are the main difference between CCDs and CMOS cameras, well, in the CCDs we have an array of detectors, and all of them are read one by one. So basically, when photon hit here, we need to wait before that all these lines ahead need to be read in order that then can be amplified, photoconvert, and then basically transfer to the software and to the computer. In the CMOS, the technology of the chip is different, and basically each of the detectors are already amplifier, so we can go really faster in the detection. The main difference between these two is that the noise in this is all the same for all the pixels, well, in the CMOS is not, because each of the detectors is amplified by itself, and this basically produces differences in the signal-to-noise ratio, pixel by pixel. But then they are very comparable in the, let's say, in the quantum efficiency. However, the chips of the CMOS are larger, and usually we can get like a 2084 by 2084 pixels in the CMOS, while in the CCDs we have on the 1000 by 1000. And the main difference is how fast we can read. Nowadays, this technology of the CMOS is reaching like 95% of quantum efficiency, which basically enable you to collect single photons, and you can work for all the applications like super resolution, etc. You can do with this kind of camera. But most traditionally, super resolution was based on electron multiply CCDs, and the main difference between the regular CCDs and electron multiply is that after the reading, they have a high voltage series multiplication that will amplify the signal and will increase the signal to noise, as you can see here in comparison with the CCDs or the CMOS, and we can have less than 1 electron noise per pixel, which is really, really good. And these are one of the most used cameras for single molecule techniques, let's say. to basically get to the final part, which is basically some other parts that we need for a confocal microscope. We need some electronics, and we need some optics. And basically, I want to cover that to move the scanner, we need electronics that can move the scanner. What we need? Well, we need an interface that is called driver that tell the instruction to the scanner to move, the x-axis will go fast and the y-axis will go gradually, going from top to bottom in the image. So this is the driver that will tell the proper information. But we need to feed the driver with another electronic, which is a card that will tell, well, move that amount of voltage in one axis and that amount of voltage in another axis. And if you can control this, well, you can do a raster scanner, but you can do also a line, you can do a circle, you can do whatever figure you want with the scanner. And this is what we do in the lab in our custom microscopes. Then we need cards to transformate the information from the detector to a digital signal. If we are working with the PMT, so analog detection, we need to use an intermediate device, which is called the contact fraction discriminator. We need to feed this contact fraction discriminator with an amplification of the signal from the detector. And what this contact fraction discriminator does is basically transform the information from analog to a digital, and this enables us to do, FLIM and some other approaches which are important. If you are lucky and you have a digital detector like APD, you can connect straight to your electronics that you will do, all the analysis that we will learn later on. Then we need optics to split, excitation and emission, to select the region or the band of fluorescence we want to collect. And there are basically different technologies. I want just to cover two. One are the interference filters, in which basically we can deposit on top of a glass different material that can interfere constructive or destructive, with the light that's coming, and it will enable, the light pass through or not, depending on the wavelength that you select. Or color filters, in which you have, molecules embedded in the glass that absorb the light and basically reduce the transmission of this light within the glass. This is an old technology, this is new technology, but this technology of the glass filters, so absorption filters, are very, very useful for some of the techniques that we will learn, in particularly the diver microscope, because we will be working with photons who are not, straight, they are scattered. And these interference filters only work if the photons are coherent, if they are coming in the direction for the one that the filter was designed. Can be 0 degree, can be 45 degree, or any. If your photons are coming in any other direction, the filter will not work, will not do the work, will enable to pass eventually light that you don't want. So the glass filters are very useful for diver. Let's see. And finally, I want to mention just quickly about some new technology that is also important for diver, which is the adaptive optics or adaptive mirrors. And to tell more about how this is, I want to stress this situation in which, well, we can have a sample, and the sample can have different compositions, different instances of refraction, etc. And when we focus our light, our wavefront, or let's say how the light propagates along the optics, will be focused. But if the index of refraction change, you will see that the photon coming from different places in the optic will get in different focus, in different position. And this is something that we can see here in this image. So this is an X-zeta stack, and you see that in the very beginning we have very crispy resolution of this alveolus, these are lungs, and in the bottom we basically blur all the image, even when you have even more photons. But the point spread function got basically broader, and basically we lost resolution. So if we can have some sort of, mirror that can modify this wavefront, so pre-compensate whatever will happen in tissue, we will basically enable that all the photos exactly same point, and we'll have, in better resolution. So this is exactly what the adaptive optic is. This is an array of mirrors. In particular, this is 111 deformable mirrors, and this is a result from the LFD, when you can see that using the dive microscope, you can go from a CT stack of 2 millimeters, and you can still have very decent resolution for a neuron like this. So finally, I want to wrap up saying that, well, some of the instrumentation we have in Uruguay most of them are commercial, in Facultad de Medicina, School of Medicine, Instituto de Investigaciones Biológicas Clemente Estable, Instituto Pasteur, and also in School of Engineering. And I will just comment the 2 microscopes that we are developing here. The first one is a 2P microscope on top of an inverted microscope, and we will using some of all this part that we already covered. And the other one is a diver microscope, which you will learn more on Wednesday by the talk of Belén Torrado. This is a microscope designed in the LFD, intended to do imaging high scattering samples. And this is a picture of the diver in the Pasteur. So we will went there and we will learn more about this technology. So with that, I would like to thank Hong Tao Chen, who is the owner of most of these slices, and I took from them for this presentation.